Okay, let's look at some examples from your homework. I actually want to start with number 7. We're actually going to kind of go in reverse order with this. So you'll notice I'm actually starting with a definite integral. If you know how to do a definite integral in integration by parts, you can do an indefinite integral. A lot of the stuff we're going to talk about in this problem will apply to indefinite integrals as well. So here I have this integral from 1 to 2 of x to the 4th times natural log of x dx. So hopefully you can recognize how, okay, I have two different functions being multiplied by each other. And I need to figure out which one's which one's my integrable function, and which one's my differentiable function. Now, I see the fact that, okay, this is a power function, which means shouldn't I set that as my u? If I do, right, I can take the derivative enough so that'll end up reaching a constant value. So eventually get it simple enough. I mean, it'll take a few different times, but it will eventually get simple enough. But if I do that, that means I have to choose natural log of x as my integrable function. What's my problem? I don't know how to find the antiderivative of natural x. Remember, if you ever have a logarithmic function, you have to choose it. You don't have a choice. You have to choose it as your differentiable function. So I have to choose natural log of x as my differentiable function, which means that x to the 4th ends up being my integral function. Do I know how to find the antiderivative of x to the 4th? I do. It's not pretty. It gets more complicated, but I do know how to find the antiderivative. So that's how I'm going to choose these. So let's go ahead and find their derivatives and their antiderivatives. Okay, if u is equal to natural log of x, then my derivative is just 1 over x. And then if dv is x to the 4th, then my antiderivative is x to the 5th over 5. So now that I have those, I can go ahead and rewrite this integral using integration by parts. And I get u times v, so x to the 5th over 5 times natural log of x. I just switched the order around. Doesn't matter what order you put it in. This just looks a little nicer. Minus the integral of v du. X to the 5th over 5 times 1 over x dx. So you'll notice right now I'm not worrying about the bounds. We'll come back and talk to the bounds in just a little bit. This first piece is already simplified as much as I can, but take a look at my new integral. That looks pretty complicated. But what happens when I multiply x to the 5th over 5 times 1 over x? This x in the denominator cancels out with one of the x's in the numerator, and I'm left with x to the 4th over 5 dx. And that's a function that I know how to find the antiderivative of. It's no longer a product of two functions. That's just a power function. And in fact, if I wanted to, I could pull out that 1/5 in front of my integral. And now that's even more simple. So even though we were forced to take the antiderivative of x to the 4th, it still ended up simplifying really nicely for us and creating this new integral that was much simpler to find the antiderivative of. Don't forget, though, that this is a definite integral, so I still need my bounds from 1 to 2. What about my piece that's already been integrated? Well, that just means I need to evaluate this from 1 to 2. So what will that look like? Well, let's start with just this piece. That means I want to plug in my upper bound, so I'm going to do 2 to the 5th over 5 times natural log of 2. I'm plugging in anywhere I see an x, minus, and now I'll plug in 1. 1 to the 5th over 5 times natural log of 1. And there's my first piece. That's me evaluating it from the upper bound to the lower bound. I'll come simplify that in a little bit. Now over here, do I know the integral of x to the 4th? I absolutely do. My integral is x to the 5th over 5. And now that needs to be evaluated from 1 to 2. Okay, this piece, 2 to the 5th. I get 32 over 5 times natural log of 2. Natural log of 2 is just something you'll plug into your calculator, or you can just leave it in exact form. That's going to give you an irrational number. Minus, well, 1 to the 5th is just 1, but what's natural log of 1? Natural log of 1 is actually just 0. So this term just goes to 0. Okay, then over here I have minus 1 to the 5th times, and then I'll plug in my upper bound, so 2 to the 5th over 5, minus my lower bound, 1 to the 5th over 5. What does that leave me with? That leaves me with 32 over 5 minus 1 over 5, so that's just 31 over 5. And I end up with 32 over 5 times natural log of 2 minus 31 over 25. And that's how I would do this problem. So once again, I had to choose natural log of x as my differentiable function, but it ended up working out really nicely, and this kind of walked through how to evaluate it with bounds. Okay, let's look at the next problem. Okay, now let's look at the problem right before this, number 6. The reason why I want to look at this one is, once again, I've got my two different functions, x cubed and e to the negative 12x. And now I have a power function and an exponential function, which already tells me that, hey, that means I want to choose my power function as my differentiable function and my exponential function as my integrable function. So I already know how I'm going to choose them, but hopefully you can see how, because u is x cubed, it's going to take a while for it to actually get down to a constant value. This is going to require using integration by parts multiple times, which means I can use tabular integration by parts to work through this one. I know what my u and dv are going to be. I'm going to choose x cubed as u, and I'm going to choose e to the negative 12x as my integrable function. And now let's just start taking derivatives and taking antiderivatives. Let's start with x cubed. When I take the derivative of that, I get 3x squared. Once again, I'm going to keep going until I get all the way down to 0. So next I get 6x. My next derivative, I get 6. And then last, I finally get 0. So with each of these, I'm just taking the derivative. So now that I know how many times I need to do this, I'm going to take the antiderivatives of the other side. So how do I take the antiderivative if I have a constant right there? You just divide by that constant. And there's my first antiderivative. But now I need to do it again. Remember, if I have a constant multiple, I can just ignore that, keep it there, and take the derivative or the antiderivative of this like normal. So that gives me 1 over negative 12 times 1 over negative 12 e to the negative 12x. Well, 1 over negative 12 times 1 over negative 12, that just gives me 1 over 144. Okay? The process, the antiderivative for this is just going to be the exact same thing over and over again. So as I keep doing this, I get 1 over negative 1728 e to the negative 12x. And then I need to do it one more time. And I get 1 over positive 20,736 e to the negative 12x. And I can stop there because now I've reached the point where my derivative is 0 on the other side. So now I'm ready to put them together. And remember, I put them together by multiplying diagonally. So that means there's going to be 4 pieces that I'm going to be working with here. And then don't forget to alternate positive and negative. Positive and negative. So let's put this all together. This integral of x cubed e to the negative 12x dx will become, my first one's positive, so I get x cubed times 1 over negative 12 e to the negative 12x. My next one's negative, so I'm going to start with that negative. Negative, and then I get 3x squared times 1 over 144 e to the negative 12x. My next one's positive, so I get positive 6x times 1 over negative 1728 e to the negative 12x. And last, my last one's negative, so I get negative 6 times 1 over 20,736 e to the negative 12x. Now, to be clear, there's a lot of simplifying that I could do from here. But if you're worried about getting the question wrong, remember, you can always just put it in like this. Put it in before you simplify it, and Pearson will still mark you correct. But if I wanted to simplify this, I could just move some of the negatives out in front, some of these negatives right here, right? I can move these out in front. And some of these fractions will simplify, so I get negative x cubed over 12 e to the negative 12x minus x squared over 48 e to the negative 12x minus x over 288 e to the negative 12x minus 1 over 3,456 e to the negative 12x. What am I missing? This was an indefinite integral, so I always need to end it with a plus c. Now there's one more problem that I want to talk about, and mostly just because there's a tricky piece to it here. This one's number 3. It's the integral of 3x times natural log of the square root of x dx. We might look at this and say, oh no, not only is this integration by parts, but it's also chain rule. I've got a function inside of a function. It's also integration by substitution. But hold on there. One of the first things to keep in mind whenever you're doing these integrals is if you ever see a natural log, just think, can I use my natural log properties? Can I use my log properties to simplify this a little bit? With the first problem we did, no, there was nothing I could do because it was just natural log of x. There wasn't anything special about the natural log. But here I have a natural log of the square root of x. And remember, that's the same thing as the natural log of x to the 1/2. We have a log property for something like this. I can move that exponent out in front as multiplication. And that really simplifies this integral, because now I'm working with the integral of 3x times 1/2 natural log of x dx. And based off our integral properties, what can I do with these constants? I can move them out in front. So this becomes this integral of 3/2 times x natural log of x dx. And at this point, you should know what to do. Now it's very similar to that first problem we looked at, number 7. But I just wanted to talk about this one real quick so that you're not confused about the square root of x. Use your log property to simplify it and get it to a point where it's manageable. Okay, but those are the ones I wanted to go through. If you still have questions on the homework, please reach out and I'd be happy to help you however I can. Good luck, and I'll see you in the next video.